Sanırım yayındayız hocam. Başlayabiliriz.
Okay.
I suppose we shall start. Good evening. I would like to welcome you to our traditional, somewhat this time conference-wise traditional Nobel Prize seminar in Metaphysics departments. I am with Professor Özgür Sarıoğlu, who mainly researches on mathematical physics, gravitation, and supergravity, if I am right. So today's topic is 2020's Nobel Physics Prize, which was parted in half and awarded to Roger Penrose, well deserved. So I guess our speaker is going to talk mainly about this part of this Nobel Prize today. I would like to invite you to the virtual conference space, so to speak. So you may start if you wish, sir.
Okay, thank you. 2 weeks ago, if you remember, the Nobel Prize has been announced, and I mean, it's always a Tuesday. The Nobel Prize is always announced on a Tuesday on the first week of October. And I was not expecting Roger Penrose to win at all. I mean, I was really exhilarated when I heard about it. So, and it was, I was really excited when our chairman asked me to give this talk. So I tried to prepare something which would be suitable for all beginning students of physics. So I have based my talk mostly on easy readings. So I have used material I found from APS physics. Here is the, I mean, I'm hoping you can see the screen, right? There isn't any problem with that. Physics.aps.org. And this source actually, I mean, for the beginners, is a really useful one. It's written with advanced undergraduates and graduate students in mind, but you can always check the site regularly and you will find really nice articles on elementary stuff. I would also recommend Quantum Magazine, which has also really nice articles on mathematics, biology, chemistry, and of course physics, and also computer science. Okay, so I have used material from these sources in my talk. Okay, here are the people, you can see the pictures, that have been awarded the Nobel Prize. Roger Penrose, of course, he's a great figure for anyone who studies gravity. He was awarded the Nobel Prize for the discovery that black hole formation is a robust prediction of the general theory of relativity. So even though we have, I mean, what he did was indirectly proving that there was no escape from singularities or black holes once you assume that the Einstein equations are correct under some mild, reasonable, physically reasonable assumptions. And the other two, and the other half, jointly went to Reinhard Genzel from Germany and Berkeley, and Andrea Ghez, a lady. So for the discovery of a supermassive compact object. So this is not a black hole. I mean, we don't have rigorous proof that it's a black hole, but it's a supermassive it's a supermassive compact object at the center of our own galaxy. Okay, so the best explanation, I mean, I will show you some pictures for what we observe is a supermassive black hole, but the Nobel Committee was really careful in stating the reason they have given this prize to these people. Okay, so as you are all aware of, the black holes have been in the spotlight. I mean, this year's Nobel Prize also has to do with black holes, and you have all seen this by now famous silhouette of the supermassive black hole that was released last year with some media fanfare, I should say. This is the famous picture of the black hole at the center of Messier 87, a large galaxy in the Virgo cluster. It's a nearby galaxy. And it's taken by the Event Horizon Telescope, which is made up of 5-6 telescopes itself, using AI techniques, artificial intelligence, and machine learning techniques. This black hole resides 55 million years from the Earth and has a mass of 65 billion times that of our sun. So this is really huge, okay? And you have all seen this picture, hopefully. Also, if you remember, the 2017 Nobel Prize in Physics was also awarded to the detection of gravitational waves. So this was long coming. So far, GR has until 2015, I should say, general relativity has only been checked in the so-called weak gravity regime, weak field regime, and observing the coalescence of two black holes was the first time that gravity was checked in the strong field regime. So so far we have quite a number of black holes that we have observed. So I should also mention that there is something new also this year. In September of this year, it has been confirmed that these are all about colliding black holes, okay? And you can see the mass range of the black holes. Previously detected black hole collisions involved black holes of mass at most 50 times that of our sun. So you can see that limit, this line here. And in fact, people who are trying to understand how black holes form by studying the nuclear processes going on inside stars and neutron stars have found that, according to the standard law, there is a theoretical mass gap between 50 masses of our sun and 130 masses of our sun. We shouldn't observe any black holes. That's like the calculations indicate that that's the case. But in September, it has been confirmed that the colliding black holes have 65 and 85 that of the sun, and the resulting black hole, the two black holes coalesce and come together, has a mass which is 150 times more than our sun. So this is also a new thing to explain about black holes. Okay. So with these pictures that I've shown you, it's fair to say that the reality of the black holes has become certain. Now we can confidently say that black holes exist. And if in these days of pandemic, it's difficult to grasp it maybe, but we have become accustomed to the idea. However, in the old days, these things were not this clear. After Einstein came up with the theory of general relativity, soon afterwards, Schwarzschild, by now many of you may know, has come up with a solution of Einstein's equations, which by now we know describes a static, spherically symmetric black hole, okay? So according to GR, general relativity, when a spherically symmetric object collapses under its own gravitational pull, there exists, you can show this mathematically, it's really easy calculation, a so-called Schwarzschild radius. That's like the event horizon for a static spherically symmetric static black hole. at which the infalling material becomes cut off from outside observers and a black hole forms. So this is what GR tells us. So a black hole is a region of space-time, roughly, where so much matter is packed within so little space, such that the gravitational pull becomes so strong and nothing, not even light, can escape from it. Okay. The spherical surface of no return for light forms the so-called event horizon, and this makes a black hole. So for a okay, maybe I shouldn't say anything technical here. So to give you an idea, if the Earth would have to shrink into a sphere smaller than, I mean, if the Earth was to form a black hole, it would have to shrink into a sphere smaller than a ping pong ball. If I remember correctly, the number is like a sphere of radius 9 millimeters, if I'm not mistaken. And for our sun, for it to turn into a black hole, it should reduce to a sphere of radius roughly like 3 kilometers, if I remember the numbers correctly. So huge mass put in a really compact area. Okay. How does the matter collapse like that? Well, under the gravitational pull, you know that gravity is an attractive force. After a certain time, the star has no fuel left to balance, if you like, the radiation pressure stops, and there is only attractive force, and the matter collapses towards a central region of zero volume, we say, which is like a point or a ring. For rotating black holes, it can be a ring of immense density, which we call a singularity. Okay. Now, before 1960s, there was this solution of Schwarzschild, but people did not really believe that there could exist a singularity like that. And so people just said, okay, there's something wrong with GR, and they didn't want to think about this. They said this singularity was absurd, and many physicists assumed that some sort of mechanism would have to prevent a star or an object from ever collapsing into some singularity. Okay. And in fact, gravity in those days was something that people did not study that much. Okay, there were only very few people studying gravity seriously. Now, this view shifted in the early 1960s when, so I'm telling you about the history first, when astronomers identified the first quasars. And these are extremely bright objects in distant galaxies with enormous energies packed in very small regions of space. So they already knew about Schwarzschild solutions. So they said, maybe these are really massive million solar mass black holes. So there was speculation. Okay. So to make all of this reasonable, of course, you really have to show that, I mean, mathematically, theoretically also, it was necessary to show that material can collapse to a point in real-world conditions without assuming perfect spherical symmetry, which was what Schwarzschild assumed. So, of course, perfect spherical symmetry is something really special, and they said, well, in real life, in the universe, I mean, things are rotating, moving, so you don't expect perfect spherical symmetry. So can you, I mean, the challenge for the theoretical physicists was to show that indeed materials in real world conditions without the assumption of perfect spherical symmetry could collapse. Okay, and there comes Penrose. He addressed this question of non-spherical collapse in 1965, before I was born. Okay, he argued and showed that any object with an event horizon, so already what he had in mind was the Schwarzschild solution. So any object with an event horizon regardless of its shape, will have to contain so-called trap surface. Okay, for the case of a static, non-rotating, perfect spherical, how should I say, object star, the trap surface and the event horizon are roughly the same. This surface has the property that if you place light bulbs on it, soon I'm going to show you a picture of this, all of the emitted light rays would converge to a point. And since gravity is attractive, all of the light rays would converge to the center point, actually. So anything inside a black hole has only one feature ahead of it, falling further toward the center. So nothing can escape, even light, which is the fastest thing in the universe, right? You know that, cannot escape this gravitational pull. So inside the trap surface, actually, space and time switch roles. Time becomes the direction pointing toward the center, so that escaping a black hole is inevitable, really. It's impossible as traveling back in time. So this was all done by Penrose under really mild assumptions. And the proof is not that difficult, actually, but one has to prepare oneself with technical stuff that one needs. Now, with Hawking later, Penrose also showed they proved a number of theorems, so-called singularity theorems. They made some mild assumptions and generalized this result, and they showed similarly for the universe, for the entire universe, that singularity would have inevitably existed when matter and energy were densely packed together in the Big Bang. Okay, so this was big. And in fact, I think it's fair to say that if Hawking had been alive, he would also have gotten the Nobel Prize this year. But he passed away, as you know, and then he couldn't get the prize. Okay, this is the picture, the famous diagram from the 1965 paper of Penrose. By the way, these diagrams, I mean, Penrose is an excellent artist. These diagrams are called Penrose diagrams, and he has also made that contribution to GR. This picture here shows the gravitational collapse of matter that happens in the formation of a black hole. So if you like, time is running upwards here in the vertical direction. And you can see here some light rays which are traveling at 45-degree angles, right, like this. And they enter the black hole, so time is running like that. So imagine the idea. So time goes that way, and light rays are traveling, and that they cannot escape the black hole, and they keep going toward the central singularity. So the singularity is here, and it is this world line, and all of the light rays are like bent towards the singularity. So this is a really famous picture, and here is the trap surface or event horizon in this case. Okay, Penrose's proof that the collapse of dying stars could naturally lead to singularities was in fact really bad news for GR, because this shows that general relativity is not complete, it's incomplete. And of course, Penrose, being a really smart person, did not want these singularities to be accessible from outside the black hole. So he developed the idea of cosmic censorship. Cosmic censorship. I'm sorry, I cannot say. I'm really tired. He has this conjecture which protects, so if you like, external observers from ever observing this singularity. Okay. Also, I mean, I should also mention that even in 1969, Penrose was an advocate for observing the skies in search of black hole influenced phenomena. He said people should really believe in the existence of black holes and like look for them, okay, in 1969. So the other two people, I talked too much about panels. I should also mention their contribution. That's also really important. What they did was to observe the center of our own galaxy, the Milky Way. The first hint that there was some compact object, if you like, at the center was detected in 1931 by Jansky, who observed a radio signal coming from the direction of the constellation Sagittarius. Okay. Later in 1974, other astronomers, Balik and Brown, pinpointed the bright and compact object in the galactic center. And now it's known as Sagittarius A star. Okay, so they were able to pinpoint, really like say where it was coming from. In the 1990s, more observations were made. They looked at other galactic centers and they observed, indirectly of course, super heavy objects at the centers of galaxies. But of course, one needed better technology and new strategies, really smart strategies to overcome that these central anchors like compact objects were indeed supermassive black holes. So here comes the other two laureates, Gez and Genzel. These people have have observed the center of our own galaxy for nearly 30 years. And in fact, they are rivals. They are leaders of rival teams. One of them, say, Gez, uses the facilities in Hawaii, whereas Genzel uses the facilities in Chile, Atacama Desert. They collected evidence for a large black hole at the center of our galaxy. So if you like, things were double checked. Being rivals, they were using different techniques and they could really verify each other. Starting in the 1990s, they have been observing the stellar orbits in the Milky Way's central region. They have used adaptive optics and really smart techniques to do this with precision. So as I already said, they use the facilities in Chile and Hawaii, and they were able to resolve single stars in this very crowded, dust-filled environment. And remember, they were doing these observations from Earth. So the problems that the atmosphere brings in are extra complicated, but they were able to overcome all of those difficulties. The observed motion of these stars implied a gravitational anchor of 4 million solar masses crammed into a region no larger than our solar system. So really, really massive stuff in a really tight place. And the most reasonable explanation is a black hole. So they have made these indirect measurements. So here I'm showing you a picture of 6 of these objects. So the corner here, this spot is the center of the galaxy. And you can see some orbits of at least 6 stars. Like they have some names, S2, S1, S12, whatever. S2 is really special. I will tell you in a minute. So just to give you an idea about the figure. So if you were to think about the solar system, some orbits of some of the bodies in the solar system, like you cannot really see it. Neptune is in there. Here has been plotted for comparison. Okay. And by using these elliptic orbits, they were able to say that they were able to calculate the mass of the black hole at the center to be like, I mean, you can see the number 4.31 plus minus 0.38 million times that of our sun. So here, here I want to show you, I'm hoping everyone can see this. In a minute, it will hopefully open up. Here, I want to show you a small video that I took from Quantum magazine. So notice that this is the state of affairs in year 2000. And I'll play the video, and then you will see how the years pass by, and then you see the orbits of the stars. The red thing you see here is some gas cloud. It's called G2. At one point, it looks like there are two stars there. So let me run it again. But it's not. It's a gas cloud. And you see what these people did. They were observing these stars. There is in the middle this really tiny corner where the center of the black hole sits. So let me run it once again, and everything runs from 2000 to 2014. I will also show you another picture where it's very similar to this one, but that one is more recent, made with more recent data. Okay, I'm showing you the same picture. Let me move one slide further, and then here comes the other picture or video that I had in mind. So this is data, this is the video made by the Keck UCLA, by the GAZE group in Berkeley. This is supposed to be the star in the middle is where the black hole is, and the data starts in 1995. I also would like you to take make a note of this arrow. I will tell you what that arrow is, and then this S02 is really special. In the previous video, it was S2. Here it's SO2.
So,
okay.
May I just interrupt a minute to notify you that the video you may try to run is not showing?
It's not?
No, it is not.
Okay, let me look at why is not showing. Let me see what's going on. I'm sharing my screen, but I do not really understand. New share, maybe I do. Okay, have you seen this previous one? Was I just talking to myself, or?
Right now, we can see a video on the screen. This
Which one is that? The first one or the second one? I thought I showed.
I'm sorry, sir. I believe we did not see both of those.
Okay, I see. So let me show you. How did I do it? That's the question. Okay. All right. Let me first show you the movie that I was talking about. Is this visible now?
Yes, sir.
Okay. So this video was starting from 2000, and in the middle is the black hole, and you see the orbits of the stars. This video runs all the way up to 2014. Let me run it again. So this is made from older data. And the red one is some gas cloud. It's called G2. And you see many stars orbiting. So these people did a tremendous job and found out all the orbits of other stars around galactic center. Okay, hopefully everyone can see this now. Right, can you see it? Hello? Have I lost you? Can you see it?
I think her microphone is disabled, and may I help?
But her picture was also frozen, so I couldn't.
Okay, she's back now.
Okay, could you see the video that I was trying to show you? And
yes.
The second video that I want to show you, it's about the same stuff, but this has, can you see it now? This should be a different video.
Yes, sir, we see a different
Okay,
video.
this is more recent. This has more recent data in it. It starts from 1995. Don't ask me what that 0.8 is. It's the star in the middle shows the galactic center. And this is S2 that you should be careful about. And here is some scale. Okay, I will tell you what that scale is. So here things run as time is passing by, and the orbits of the stars around the galactic center you can see. The yellow one is the special one. That's the S2 or SO2 in the videos. So it's running 2014. This is more recent. I told you so. The orbit closes, so you have a perfect ellipse there, and other ones. So let me run this one again. So in the beginning of the video, you can see the yellow orbit for S2 or SO2. And here things run again. Okay, in all of these years, almost 25 years, 30 years, these people have been dedicating their lives to taking a snapshot of the galactic center. And they have come up with this beautiful video. Okay, and they are still actively working on this problem. So let me go back to, I'm not sure whether you can see this or not. So I'm trying to go back to what I had beforehand. So hopefully this is fine now. The latest animation shows that, I mean, if you like, the two animations or videos imply that the stars are gravitationally bound to a supermassive black hole with a mass 4 million times that of the sun. I told you that the data was collected by Guess in UCLA. Oh, I said Berkeley. I think it's UCLA in Los Angeles. In over 25 years, the star SO2, as I said, is special because it completes a full orbit in about 16 years. And the vertical arrow that I showed you before represents this much of space. So it's a really, really tiny spot out there in the sky. So they were really able to pinpoint the galactic center. Okay, the upshot of all of this, so I shouldn't really, I've already taken a lot of your time, is that these are fascinating times for trying to work on a more complete theory of gravity. We know that GR is incomplete. It needs to be corrected in some ways. Gravity needs to be quantized, that's another thing. And also fascinating times to study cosmology and to try to understand how the cosmos works. Okay, this is all I want to say, and thank you for listening. I hit some technical glitches, but hopefully you can forgive me for that. So maybe I keep my screen on the presentation, or maybe I get out of it. I stop sharing and people can see me. I don't know. Any questions?
Thank you, sir, for your presentation. Yes, we do have some questions.
Okay.
And I can ask them from like a chronological order or reverse as you wish. Thinking that some people you just all right, so I'm going for the chronological order. So the first question was given by one of our viewers. Why was there a theoretical mass limit for black holes? This question was
okay.
given.
It's about okay. Black holes should form by collapsing stars, right? And you know the chemistry going on inside. Oh, there's something going on. Oh, okay. roughly understand the chemistry going on inside a star. So, I mean, fusion and all, stars are places where you, if you like, make the elements slowly. I mean, first the hydrogen and then the helium, and comes the other elements slowly. So for fusion, I mean, you have to use some fuel. The star has some finite amount of fuel. And with all the models, I don't really know in detail how they do it, but they let the initial conditions run, and they end up with black holes of masses that are 50 times that of our own sun. And they cannot explain, they cannot, when they run the machinery, I should say, they cannot end up with, they show that they cannot end up with black holes of masses between 50 and 130 masses of the times the mass of the sun. Okay, so the observation in September, just last month, was quite a surprise in that sense. So we have to, theoretical physicists have to find a mechanism, some chemical processes, which allows intermediate mass black holes, we say. Okay, so this is an open question, but it comes from the calculations. We don't know how a black hole of solar mass that is between the range 50 and 130 can form, but we have observed two colliding black holes. One of them has mass 65 and the other one has 85. They come together, they release some of their energy, and finally a black hole of mass 130 forms. Okay, so we don't know how the two ingredients, I should say, 65 and 85 times that of the solar mass black holes formed in the first place. That was what I was trying to explain. We don't know.
Well, thank you for your answer. I will move on to the second question.
Okay.
One of our viewers again asks, why collapsion of a dying star leaving singularity is bad news for GR?
Because that means we have a singularity in space-time, the fabric of the universe, right? There is this thing, we don't know what that is, but it must form according to the equations. But if, in some sense, GR, the equations for GR are no longer valid there at that singularity, right? It's like you are trying to, you are dealing with an equation like 1 over z, and z is going to 0. You are, of course, in trouble. Things become divergent. You can no longer trust the equations. But somehow, the universe is there, and the equations need to be corrected in some sense. That's bad news for GR. That's what I meant. That was what I was trying to say.
Oh, thank you, sir. Yeah, that is definitely bad news for GR, as it seems.
It's incomplete, but I mean, well, I mean, you have to understand the unit of physics picture. I mean, we have theories which are valid in their region of validity. We still use Newton's theory, which we know is wrong, but it works perfectly fine inside the solar system. So we don't throw it away. Likewise, we don't throw away GR. We just know that we have to be careful with it when it comes to dealing with these singularities. It needs to be completed. It's not the full theory.
Sure, and obviously GR is such a perfect theory to just throw away over this thing. Another question is that why are all orbits around black holes ellipses? So,
I don't know, but there's also the line of sight thing, right? So we are looking at these orbits with some angle, right? We are not really positioned in a perfect way so that they are all circles, for example. I don't know. I mean, there's this angle, right? Observation twice. This is a question that I would not really. I mean, think about a circle, right? And then rotate it. Then it begins to look like an ellipse. That's the reason. There's some angle with the line of sight. Right? Line of sight.
This one was easier to explain. And the fourth question is a little bit of a gossip type of question, if I may add. Is that the question is that why this Nobel Prize has been given to Penrose instead of Landau or Ray-Choudhury, who made the more fundamental discoveries about the field at the time. They ask if you find this Penrose being awarded with the Nobel Prize even fair. That's their in question.
I couldn't catch the names of the other people that was suggested.
One is Landau, and if I am, Landau. The viewer asks, why isn't the Nobel Prize is awarded to Landau and Ray-Choudhury? If I am pronouncing the name right.
Choudhury. Well, they also did important things, obviously, but I don't know. You should ask that to the Nobel Committee. But Penrose certainly did something which is really important. I mean, it was an important thing. No one thought about this beforehand, and the proof is not that complicated. If you make the necessary preparations, Ray-Choudhury equation, and it starts with the geodesic deviation equation, and then you from there you go to the Ray-Choudhury equation, and then you work with it, and then you come up with this stuff. So the proof is not that difficult, but you have to learn a lot before you can understand the proof. But it's a really neat idea. So I don't know. That's the Nobel Prize Committee. But I'm happy that Penrose got it.
Thank you for your answer, sir. And another question is that this question is more about our viewer asks, how can I visualize a black hole in my head? He asks, what is the closest description you could make to a black hole, imagining a black hole?
Well, I can give you a two-dimensional example, and this is sort of standard. Take some bed sheet, right? Ask your friends to pull from the corners, from the four corners, and make it really taut. And then take a really, really heavy iron ball and throw it on the sheet. Okay, then it will come down like this, right? So imagine the ball being really, really heavy, and then it will be really bent, right? So if you throw another ball towards this ball at the how should I say steel ball in the center, say, the ball, depending on the velocity, can pass near the bent sheet, or it may even fall into the sheet, right, into that thing. So this is a two-dimensional example, but imagine this happening in 3 dimensions, in 3 space dimensions. There's also 1 time dimension, but so it's difficult to imagine because I don't know how to draw pictures and like that. But not even light can escape from that. So it's really like this heavy ball at the center of the bed sheet. It's really like that. I mean, imagine that in 3 dimensions. Was that helpful? I don't know, but that's the best way to imagine a black hole.
Thank you, sir. Another question is that if we consider the infinitely strong gravity of the singularity, does the Penrose theory still hold?
No. There's no such thing as Penrose theory. What Penrose does is he proves some theorem. He said, okay, under mild assumptions, weak energy condition and some other things. It's a little technical, so I don't want to say about those, let's tell those things, which are really reasonable things, then Einstein's equations imply that there must form a singularity. I mean, there is no escape from it. So even the geodesics of light has to focus at that singularity. So it's a really, it's just a theorem. Under these hypotheses, this must happen. And the hypotheses that you are starting with are measurable things for Einstein's theory. Einstein's equations hold some energy, some condition on the energy matter distribution, and then a singularity must form.
Okay, thank you, sir. Another question, if I may continue with the questions.
Okay.
Another question is that, can we think of the trapped surface as a usual curved surface in 3 dimensions? Or is it something much more abstract relating to the space-time inside the event horizon?
The trapped surface is a 2-dimensional closed surface. Okay, roughly. So the easiest way to think of it is like this. There is no real physical boundary. It's if you think about a perfectly strictly symmetric and static black hole, I mean, then the trapped surface is just going to be a spherical surface. But then there is no real physical boundary. I mean, once an observer falls into that, then there is no coming back. That's the thing. I mean, I don't want to give any technical definitions, but I mean, it can all be made technical and really rigorous. So it's just a 2-dimensional closed surface in some sense.
All right. Another question. This is a little bit of more of a real query, if I may say. She asks, how do the stars in the video who were like looking really close to the black holes, how do they escape the black hole? She asks.
We are not falling to the sun, right? It's the same idea. So eventually, when they run out of fuel, they may be eaten by the black hole. Last week, there was some video in New York Times or somewhere where they took a video of, or took pictures of a star which was eaten by a black hole. So these guys still have some velocity, so they are not falling into the black hole. It's just like us orbiting the sun. We are not falling into the sun, right? We are, but we are not. We are moving on this orbit, elliptical orbit. So are they. But when they run out of fuel, right? Or I don't know. I mean, the black hole at the center may eat other stars that are not shown in the video because they cannot stand light. And then it becomes larger, and then it pulls stronger, and then maybe S2 will be gone in the next 50 years. I don't know. Was that helpful? I don't.
I see, yes. So someone also asks that. So someone asks, what does it mean for a black hole to have spin or charge? What exactly is spinning of a black hole?
Well, imagine the bedsheet analogy that I gave. Suppose you have thrown the iron ball or the steel ball into the bedsheet, and suppose the people holding the sheets start running in tandem, okay? And then in the middle, I mean, it will twist a little, right? So there will be some angular momentum in some sense. Okay, it will be rotating. We can rigorously define rotation, but I mean, this is not the place to talk about it. So then it will have spin or angular momentum, and then it will be an axially symmetric black hole. So we can, it's as if the black hole, I mean, is not just sitting there. It's also doing some rotation. In fact, you can describe, classically, you can describe a black hole by only 3 parameters. Its mass, its angular momentum, and its charge, electric charge, and that's all. So we say a black hole has no hair in the sense there is no distinguishing feature of a black hole from another one. It's just these 3 numbers. So you don't have too many options.
Thank you again. And another question is that about the type of the black hole in the center of our galaxy. Like, what type of black hole is it?
It's a supermassive black hole, we say.
It's like this viewer asks what kind of a supermassive black hole it is. It's like, is it a Kerr black hole? It's like,
probably yes. But I don't know about its spin. I mean, yeah, okay. For all practical purposes, assuming that it's static, you can explain many things, but probably it also has some spin. We don't know about its charge, as far as I know, but probably it also has some charge. Those are, as far as I know, those have not been measured or attributed to this black hole. So it may be, it's probably a Kerr black hole, but I don't know.
thank you for your kind answer. Another viewer asks, what happens to the energy that occurs from the collisions of black holes?
They go into gravitational waves, and that's those are the ripples that we are measuring in LIGO or these gravitational wave detectors. So it's just like radiation from a light source, right? I mean, there's light coming to us. So just like light traveling, you also have ripples of space-time. That extra energy goes into those ripples. They travel in all of space. And here we measure those ripples. So as a gravitational wave passes through a ruler, the size of the ruler changes, and we are measuring that roughly. That's the idea. Because space-time gets distorted, right?
I see, thank you. Now, I am quickly going to look through if we have been, if we have answered all the questions that had been asked throughout the session. Someone have asked the question, but it seems like one that we had answered. Sarpalgan asks, is that an idea that the 2 collapsed black holes you mentioned were each of them formed by 2 collapsed black holes?
Each of them? Sorry, I missed the last part.
Yeah, it's he asks
65 and 85.
Yeah, 65
times,
and 85 times black holes was formed by 2 black holes with 35 and 50 times mass of the sun. He asked, like, do we know?
That has been confirmed.
Yeah,
they have measured the masses. They have some templates. Okay, they change some parameters, and then they say if 2 black holes coalesce, come together, right? With masses m1 and m2, say, they keep it general, they calculate the ripples they are to see by solving Einstein's equations numerically, though. And then the wave comes, and then you measure it in your detector, and then you look at the templates, you say you fit the signal you measure with what you have done. And then from that, you can deduce the masses of the original black holes. And that's those are the numbers that fit perfectly into the templates, I should say, calculated from GR. That's how they find the masses.
Okay. So I think we have been through all the questions so far, and this was a very fruitful session, and evidently 2020 was a very fruitful year for physics, at least.
Okay, yeah, I mean, not for our lives, but I mean, we have turned into a Zoom university, not an ordinary university, but okay.
Yeah, like as it seems that they had to reward two different topics for the Physics Nobel Prize. Would you consider 2020 as a fruitful year for physics?
Yeah, but I mean, these works were done already beforehand. So 2020 is the year the Nobel Prize was given. So, I mean,
Yeah.
hopefully, I mean, yeah, I can say that. Yeah, I see your point, but okay.
So thank you very much for your kind attendance to our seminar that hosted by Metaphysics Society, and I would like to thank you to everybody who had listened. We have about 75 people who are watching on the YouTube. So
Okay, thank you.
I'd like to say thank you to everybody and good evening to everybody. So